All right, so I think it's time for us to get started. Morning, everyone. Thank you for joining me this morning. My name is Kornafeld. I'm a software engineer at Moov. I work on card payments, and my team specifically owns services handling OCT and AFT card transactions. I'll talk about what those are later. I live in Boston. But you can probably tell that I don't have the quintessential Bostonian accent. Reason being is that my roots go back to Hungary. So in this presentation, we are going to revisit the journey that my team took while implementing OCT and AFT card payments. We will learn how one idea can lead to the next and celebrate challenges that let us software engineers get in the flow while dealing with them. We'll also remind ourselves that keeping the solution simple is a constant North Star in our profession. And we'll also geek out a bit with numbers. And before I forget, I do see some of my teammates in the audience. They are probably here because they know all too well that there is no Adam giving a presentation without someone in the audience winning a pizza. So if you like fintech and pizza, you came to the right place. And if you like, where's the screen? Was that me? I didn't touch anything, I swear. It was you.
Yeah, that's freaking weird. It was good and then it just boom, it's gone.
There we go. Maybe my computer doesn't like pizza. So yeah, if you maybe like fintech but not pizza, well then maybe the solution that I have for you is that there is an awesome presentation next door titled How Fintech Developers Can Engage Large Corporations by Alan Torres. But I can't guarantee you that there is no pizza there either. So, all right, so a few definitions, what OCT and AFT is. These are instant varieties of card payments. Just to put things in perspective, the total instant payments volume is expected to go from 74 billion to 235 billion in the next 3 years, according to Juniper Research. And so OCT stands for Original Credit Transaction. This is when funds get pushed onto a payment card. And for all intents and purposes, when you look at it like behind the curtain, it just looks like as a refund. So this is when the card brands are actually using or reusing legacy technology for novel means. And the term original in the name refers to the fact that even though it looks like a refund, there is nothing really refunded here. So this is the original movement of money that takes place here. AFT stands for account funding transaction, and this is when funds get pulled from a payment card. And for all intents and purposes, this is the reverse direction of OCT. So a couple use cases, and I'll have to cheat here because I can't remember this much. So AFT use cases are funding digital wallets, moving money into savings accounts, adding funds to prepaid cards, and funding peer-to-peer transfers, while OCT use cases include commission payouts, expense reimbursements, disbursements of loan and insurance payouts, as well as sharing economy payouts. So both of these technologies, OCT and AFT, actually requires payment cards that support these features. So the question is, how do we know if a payment card supports these? And so this is where card features come into the picture. So card brands publish files with PAN ranges and feature flags. So PAN is just the account number that's printed on the card, and So such a range looks like what you can see on the screen here. The number on the top ending in all zeros is the lower bound of a range. The number on the very bottom ending in all nines is the upper bound of the range. And I just put in the number in the middle is actually just shy of 1 trillion. That's how many numbers actually fit into this range. And so kind of like these range minimums and maximums are provided as 21-digit numbers in this example. But pans usually range from 14 to 19 digits. So kind of like the first hurdle that we have to tackle is that how do we establish a relationship between a pan that is less than 21 digits and these range boundaries which are 21 digits. And so we could trim the range boundaries. Let's say that we have a pan that is 15 digits. So we could just cut the end of these ranges to make them 15 digits, but then what if the pan we are looking at is 16 digits, then we would have to cut differently, and that would just cause the problem space to multiply. And that's seldomly a good strategy. We software engineers like when we can actually shrink the problem space. So a better idea is actually to append the pan that is of interest to us to actually make it 21 digits. So we just append zeros to the end. And then, if we do that, we can just actually establish a very simple mathematical relationship between the two is that we are looking for an account range where the range lower boundary is less than or equal to the pan in question, or as well as the range upper bound is greater than or equal than the pan in question. And if we do find such a range, then we'll actually be given Boolean flags that denote if this specific card number or payment card number falls into a range that supports either OCT, AFT, or both, or neither. All right, and so this actually brings us the main problem that we are trying to solve here today, is that this card feature lookup, when we are trying to determine if the card supports OCT or AFT, lies on the hot path. So what is the hot path? This is code execution that directly affects the customer. So customer is actually waiting on the other end to see if their card has been added to the system. And so a myriad of operations need to be carried out during linking a card in the system, of which this is just one check, one check. So lookup time is of the essence for us here. And so before we actually can do the lookup, we would have to store the data. And on the screen here, you just see an oversimplified example of how such a database table might look like. You know, the data is actually very structured, so like a relational database lends itself great as a storage mechanism for us here. And so this table would just have 4 simple columns: a range minimum, a range maximum storing the boundaries of the range, and 2 Boolean flags for OCT and AFT support, which can either be true or false. And so, you know, whenever it comes to designing database tables, it's not enough to just think about the column names. It's also important to consider the data types. And I did mention that the flags for the feature support are just Booleans, but what about the range minimums and maximums, the range boundaries? So this number on the top of this next slide here should be familiar to everyone. Yes, no? So this is the maximum value that the 64-bit unsigned integer can represent. And maybe if this was not too familiar, then the little sibling of this might be more familiar, which is just half of this -1, and that's the maximum value of the 64-bit signed integer data type can represent. And the -1, there is the space for the sign, obviously. And so the signed flavor of these numbers can represent numbers up to 19 digits, and the unsigned flavor can go up to 20 digits. And this brings us to the kind of like the next hurdle that we have to tackle, is that the card brand specified the account range for us as 21-digit numbers. So what do we do? Well, so most modern database engines do have numeric or decimal data types that with precisions that can go up and beyond the 20-digit limit. of the 64-bit integer. And so you might wonder why most of these actually go up to 38 digits. Why is it not 35 or 42 even though we know that 42 should be the answer to everything, right? So the reason being is that 38 is actually 2 times 19. And so what happens behind the scenes here is just they take 2 64-bit integers, stack them together, creating a 128-bit number, and that can represent numbers bigger than these. But whenever you go beyond this precision limit of 20 digits, these database engines usually also warn you that your storage requirement will increase twofold, because now you're storing 2 numbers instead of just 1, as well as your query performance can be degraded because most computers these days run on a 64-bit architecture, so if they have to deal with larger numbers than that takes extra CPU cycles. And so this is just a great example of why I think it's exciting to work in fintech as a software engineer, because you will be challenged with less conventional problems to solve. And so the next hurdle is that card brands publish these data sets every once in a while, and so we need to be able to load this new data set into our database without blocking any concurrent feature lookups, because as you can imagine, this is all deployed in a production environment, so cards are linked all the time, and so these card feature lookups are coming in, and so whenever we get the new data set, we have to figure out how do we replace the existing data set with the new one without blocking any active lookup queries. And there is possibly many good solutions for this. The way we did this is that we introduced a second table. We call this like a metadata table, which had just like the file name, a bunch of other information, as well as a flag that we call like active or most up-to-date or latest. And so obviously, at any given point of time, we would only set one of the rows here to true, being the latest, and then we establish a connection between the 2 tables with like an ID type column. And so this actually brings us to this very simple query that then we can use to look for these card features. So we are selecting the OCT or AFT columns from, let's say we call the table ranges, and then we are joining on the metadata table, which in this case is called files, based on the equality of the file ID, and we are filtering based on the range minimum column being less than or equal to the card number that we have in hand, as well as the card number being less than or equal than the range maximum, and we are only interested in rows of the ranges table that belong to the latest file. And so once we have this query, we obviously ran a few tests just to have a feel of how performant it is. And we have been seeing 2 issues, that the performance was fluctuating big time. We've been seeing queries running for anywhere between 1 to 3 seconds and occasionally going even above 3 seconds, which is just unacceptably slow for us at this point. And so the takeaway here is not that this specific database engine is slow for these type of queries. So for that matter, I won't even mention the name of the database engine. The takeaway here is that I'd like you to walk away with is that how do we deal with curveballs that the tools that we are trying to use may throw at us. And so, after kind of like exhausting the usual suspects of putting indexes on the range boundaries columns, another idea to try is to see if the database engine has any features that may aid in making the queries more performant. And in this case, we actually found 2 of these features that we thought might be worthwhile to try. One of them is called table interleaving, which is just, so this is the distributed database up in the cloud. And with table interleaving, we can actually physically collocate tables that share a parent-child relationship. And in our case, the metadata table as well as the ranges table are exactly in this parent-child relationship. And so this way, we're just telling the database engine that, hey, please make sure that you put these two tables in the same data center and possibly in the same disk, so that whenever we are running that query, we are not losing out time on having to fetch data from the different data centers. And the other feature that we found is the ability to store data with the index. Obviously we are indexing the range min and max values, and with this feature, we could actually specify that, oh, we want these two Boolean flags, the OCT and AFT flags, to be stored with the index. So in case there is an index hit, the database engine doesn't have to go out and fetch the corresponding row, but the data is readily available in the index, and that also can save us some time. And so unfortunately, none of these seem to have caused a giant leap in the query performance, though we did see some improvement. So what do we do next? And obviously, it might be worthwhile, to try to put some effort into optimizing the query. But before we do that, I think a good idea is to actually try to sort of like establish a baseline before we put any effort into trying to optimize. And so the question here is that how can we learn what is the best achievable performance? And so for that, we can actually construct an evil sort of like card number that actually falls right on, let's say, the range minimum of one of the queries. Because if we can do this, then we can simplify the filter part of our query to be, so first of all, we can throw away the concern of the range maximum, and we can actually replace the less than or equal operation for the range minimum to be hard equal. And the rest with the active flag remains the same. And so this change actually surprisingly brought down the query performance to the sub-second range. So this gives us a good idea whether it would be cost-effective to spend more time with this or not. And so we did actually thought that it might be worthwhile to pursue this idea. Bit of a cliffhanger before we continue. Mentioned we'll geek out with numbers a bit. You might ask the question like, what is a PAN after all? And I mentioned to you that this is actually just the number that's printed on your payment cards, be it debit or credit cards or even prepaid cards. And so, we are all in the fintech conference, so if we put our fintech perspectives, then when we look at a card number like that, what we would see is things like issuer identification number, major industry identifier, bank identification number, individual account identifier, as well as check digits and Luna algorithm. And so for those of you who don't work with cards on a daily basis, I'll just mention the last one, the check digit. So this is the last number of your payment card, and the Luna algorithm, named after the guy who invented it, is used to calculate it. And so this digit is actually useful whenever you're playing maybe a telephone game with your payment card, and maybe you're trying to make a reservation over the phone, and you dictate your card number. The other party can actually run the Luna algorithm on all the numbers except for the last one to see if they can come up with the same number that you specified as the last number. And if yes, then they can make sure that the number was captured correctly. And if not, the algorithm will actually not tell where is the mistake, but it will tell you that somewhere some of the numbers is not right. But what if for a second we actually put on our math hat and look at a card number? What do we see there? Well, it's just an inconveniently large number, right? How inconvenient, you might ask? Well, let's say that you have a PAN that starts with, let's say, 4321. So if you're reading out this number loud and it makes you say like 4,321 trillion, that's inconvenient, right? So we also kind of like when we were geeking out with this, we asked that, hey, can actually, because this is just a large number after all, so we were wondering, can this actually fulfill, so can a number fulfill the Luna algorithm at the same time, meaning that it can be a potential card number as well as be a prime, because we all know that prime numbers are special, right? And so the Luna algorithm itself doesn't put any restriction on what numbers the output can be. So anything from 0 to 9 can be the check digit of a card. But prime numbers this big, as we all know, can only end in 1, 3, 7, or 9. So just out of curiosity, we put together this small script that would actually run a range of numbers. In this example, the range contained like 99 billion numbers. And so the small script actually ran the Loon algorithm on all of these numbers. And then of those that actually passed the Loon check, we'd also do a primality check. And it actually made sense to do it in this way because the Loon algorithm is much less computational intensive than doing a primality check. And what we saw is that of these 99 billion numbers, about 4 billion is actually a potential card number in this range. And of those 4 billion numbers, about 265 million is actually also prime. And so obviously there are like an infinite number of integers as well as an infinite number of primes. So normally you can make statements like, oh, X% of numbers are prime. But in this case, because we fixed the range to be like a finite series, we can actually see that about 6% of card numbers that are potential adver could be prime numbers. And so you might think that, you know, black credit card made of metal with a built-in concierge is cool. Well, I beg to differ. I think if you have a card number that has a prime number printed on it, that's way cooler. I'm unfortunately not one of the lucky ones who carries such a credit card, but I did put together this small script that you can find on this GitHub link here that would actually run this check for you. Source code is there. It's available in Go and Python. And you can use this to run this check on your computer, and the source code is there as well, so you know that no shenanigans would be going on with your card number while you're doing this. And if you do happen one, I would actually highly encourage you to check. And if you do, I'd love to meet you, because I mentioned I'm not one of the lucky ones. All right, so moving on. My team did try to pursue this idea that I mentioned of trying to sort of like optimize the query using just the range minimums, as well as using the hard equal operation instead of the less than equal. And we did come up with a possible implementation, but I will not go into the details of that here because at the end of the day, it turned out neither simple nor easy to reason about. So at this point, we've come to the place where we concluded that we will not be able to use the database engine to be able to support our card feature lookup queries. So what can we do then? Usually, when it comes to this, the next usual suspect to try is let's put this stuff in memory and let's see what we can achieve there. And so obviously a North Star is still the need to be able to do fast lookups. So a map or dictionary type data structure comes to mind. But then you ask the question, like, what would be the keys here? And maybe a combination of like the range, minimum and maximum values would be able to create like a compound key, but that doesn't sound too simple. So here, we instead sit down and think a bit and actually come to this light bulb moment where we can actually realize that, hey, these ranges actually constitute like ordered disjoint sets. What does that mean if I try to translate it in plain English? That just means that the maximum of any given range is less than the minimum of the next range. And this is great for us. Why? Well, because this property of the data set makes it strictly monotonic. And if you think about it, it kind of makes sense as well because if it would not be strict, then it would allow for overlaps. And such overlaps could actually yield contradicting card features where one range may specify that, oh, this span or this range supports maybe OCT, but the overlapping range might specify that it does not. And so this is great for us. Why? Because this is actually makes the set sortable. And why is the sortable property good for us? Well, because this probably one of the simplest and greatest algorithms that we all learn about when we go through our computer science studies is the divide and conquer algorithm. And so one of the implementations that does this is the binary search. And so we can actually apply this to our problem by first reducing the complexity by dealing with only the range minimums. So we're still kind of like bringing forward that learning that we learned from when we were trying to do the database optimization, that, oh, we can actually set the maximums aside for a second, so that then the problem becomes like finding the account range with the largest lower bound that is still less than the PAN or payment card number of our interest. And so to be able to do that, first we have to sort the ranges, and we can do that as we learned. So you see on the screen here just 2 lines of code in Go sorts it, because any modern language comes with these sorting algorithms built into their standard library. So this is great for us. And then binary search, Go is also happen to have this built into a standard library. So just 2 additional lines actually gets you the binary search. And then once you run this and it says that, oh, here's the match for your payment card number, then we only have to do one additional check, comparing now the range maximum, making sure that the payment card number actually falls within the boundaries of the range. And if yes, then great, then we can make inferences of what the support of this payment card in terms of OCT and AFT is. And if not, we just learned that this payment card number falls outside of any of the ranges that that these ranges specify for us. So we don't know what this is, what this payment card supports in terms of these features. And again, I think this is just an ode to why it's great to be a software engineer and tackle problems with simple solutions. And maybe if you're like watching a recording of this and you're still studying computer science and wonder why they grind you with algorithms and data structures like binary search, well, this is why. Because there are actual real problems out there that are solvable by these algorithms, and this is great. So with this, we've actually able to achieve feature card lookup performances in the couple hundred microsecond range. And this screenshot that you see here is from our telemetry, showing that there is a service named Card Gateway that is responsible for handling the cards that flow into the system. And this service is actually making a gRPC call to this other service that implements this feature lookup for us. And you can see that the feature lookup takes about 300 microseconds, whereas the gRPC request takes about 3 milliseconds. So it's an order of magnitude slower to actually go through the network than to fetch this. And so at this point, what we have is this implementation that works on my computer, right? So I can finish talking here. We can just point production to my computer and that's it, right? Well, chances are that the software that we implement these days is actually going to be distributed or deployed in a production environment. And so So another takeaway is that the simplest of solutions deployed in a distributed environment can still throw you curveballs at the unsuspecting engineer. So we will take a look at a few examples of those next. So first thing first, when we moved the source solution from the database to memory, we technically implemented a cache. And caching in a distributed environment is hard. Caching in general is considered one of the hardest problems in software engineering. So one of the issues that we have to deal with is how do we invalidate the cache? Like how do we swap new data when it comes without causing any downtime? Because you still have to remember that this is deployed in a production environment where these cards are linked on a continuous fashion, and these card feature lookups are taking place all the time. And the other is that chances are that if you're dealing with a distributed environment, that you are running multiple instances of your service. So how do you make sure that all your instances actually get notified when new data becomes available? So let's look at those two problems one by one. As I mentioned, so periodically we get new data set, but concurrently there are read operations. And so you must pay attention to concurrency here. And again, just a note to Golang, this is just such a neat little language that it comes, I think this is also built in to the standard library, these looking primitives that you can just put in place very simply. And so in the code example here, this is the swap operation when we are actually overwriting the cache contents with new data. And so before we actually do the write, we just lock this locking primitive, and after we finish writing, we unlock it. And we do the same with our get or our fetch operations. This just makes sure that in the event that in this cache writing operation happens to happen at the same time that we are trying to read from the cache so that no data corruption occurs. And so another thing to consider is that let's say that we already have the cache up and running, and so this new set of data arrives. And then we ask the question, like, let's say that the dataset takes up X amount of space in memory, and as I mentioned, here's your chance to win the pizza. So like the question to answer is that how much memory should we allocate this, to the service to make this work? And to make the answer easier, I will help you that much that your answer can be either X or Y. And if it's Y, then the Y actually means it's either less than X or greater than X. Anyone? Come on, it's
less than X.
Let's do X? Okay. So technically you are right. And yeah, I still give you the pizza, but let me tell you this much that let's run this thought experiment, right? So let's say that we want this cache up and running for exactly 24 hours, right? And let's say that the cache swap operation, or like invalidating and putting new data into the cache, takes exactly 1 second. So when you say that we should allocate X amount of memory to the service, you are actually right for 23 hours, 59 minutes and 59 seconds of the day. But for the 1 second when you're actually trying to update the cache, what you would do is that you would load the new data into memory, and then once that loading is complete, then you would swap the contents of the two. So for that 1 second, you actually have 2 instances of the cache in memory, so that actually doubles your memory usage just for that ephemeral operation of updating the cache. And you might say that, well, computers these days have just gazillions of amounts of memory, so why do I care? Well, because most likely this is a distributed environment running up in the cloud and maybe orchestrated by Kubernetes, and when you do that, the configuration will actually usually specify like a much less amount of memory that is available to your service than compared to what memory would be available in like a hardware setup. All right, so this is a great pizza, congrats. So it's all downhill from here, so bear with me just a couple more minutes. So what about the multiple instances? So chances are that in a distributed environment, you might be using eventing to solve your inter-service communication. And so if you have multiple instances of your service running, chances are that all those instances are actually assigned to a single consumer group. And if you'd actually decide to use eventing to solve for this signaling, then what might end up happening is that the event comes in, notifying that, hey, there's new data, and one of the instances will actually, that belong to the same consumer group, will consume that event, and all the other instances would be left in the dark, wondering if there is no data, and they will just not know. And so I guess you can hack your way around this by separating the instances into their own consumer groups, but I don't think that would be considered best practice. So in your case, we just actually schedule the cron task with all of the instances separately. And yes, this puts a bit of a delay between when the data actually arrives and when the caching happens. But for our use cases, as the majority of the ranges do not change over time, this was an acceptable compromise. And our price, again, was simplicity. And so, how are we on time? Oh yeah, great on time. So my takeaways for you is that data might not always be lending itself to the common off-the-shelf data structures or algorithms on first sight, but you should, I think, spend some time still trying to see if there is a way to apply a transformer. You know, everything is about transformers these days. To see if applying such a transformation can actually get your data into a shape or form that makes one of these off-the-shelf simple data structures be applicable to them. Also, keep it simple, don't overcomplicate. I think you will thank yourself 6 months from now when you revisit your own code and wonder who the heck implemented this or wrote this slide. Also, distributed environments are always trickier than what meets the eye, so tread carefully. And finally, embrace the challenges, and your reward will be being in the state of flow that I think software engineers like us do like to be in all the time. And with that, I think it's time for me to stop talking. Thank you for joining me today for this opening act of the keynote presentation by Kelsey Hightower. Be sure to attend his keynote. Big thanks to Moov and the sponsors for making this event a reality. And please come to talk to me after if you have a credit card with a Prime number printed on it, or if you have any questions. And if you don't want to talk business, we can also chat about bikes and sourdough breads. Thank you very much.